Now, I would like to make some remarks on our theorem and its proof. First of all, it follows from this proof that h plus 2 of h, which is the lim-inf of a non-negative number, will be non-negative. So let me copy it down here. H plus twice of opposite h is greater or equal to 0. That is our first remark. And second, if you look at the conclusion of our theorem, which says the probability of an happening infinitely often is greater or equal to 1 over h plus twice of opposite h. You see from here that this reciprocal of h plus twice opposite h must be bounded above by 1. So 1 over h plus twice of opposite h must be bounded by 1. And this, combining with the first remark, tells us that h plus twice of opposite h must be greater or equal to 1. If you just look at the assumptions of the Petrov theorem, you don't see whether h is bigger or equal or less than or equal to 1. It is possible that h is a small number, but in order to guarantee that this guy is bounded above by 1, when h is very small, alpha of h must be positive. However, on the other hand, if alpha of h turns out to be non-positive, if alpha of h is less than or equal to 0, then we have h is greater or equal to 1 by the first two parts of this remark. Now you might be interested to know why we are making those remarks like in high school level mathematics. That is because we want to avoid the confusion when we state the following corollary. The corollary says, if the summation from n equal to 1 to infinity of p of an's is equal to infinity for a sequence of events a sub n, and the probability of ai intersection ak is bounded by h times the probability of ai times the probability of ak. For all ik greater than n with I not equal to k, and for some constants h greater or equal to 1 and n assumed to a positive integer, then we have the probability of lim sup of an as n goes to infinity is greater or equal to 1 over h. Actually, Petrov introduced this corollary first, and then he generalizes to the theorem. Here we are doing this in the reversed order. We first do the theorem and prove this corollary. So let's prove it. Recall that alpha sub h is the infimum of this quotient, as in the theorem. Now let's see what those hypotheses will tell us about alpha sub h. Let me first emphasize that those hypotheses does not mean that the inequality is true for all but finitely many alpha k with I not equal to k. It is possible that where I is small, k is big, and then this inequality still fails. So this hypothesis is about all but infinite many I and k's. Okay, now let us split alpha in terms of this hypothesis into two parts. For the first part, we are only going to consider the summation over ik's where I is greater or equal to 1 and less than or equal to capital N, where at the same time k has no more restrictions. It can be any number less than or equal to n and strictly greater than I. This is the first sum. For the second sum, we will consider the summation where I now greater than capital N, less than k, and k is less than or equal to little n. And you can easily see that those two sums really add up to be the original sum. As you can see, in the second part, is negative by our hypothesis. Because by our hypothesis, P of AI intersection AK is bounded about by h times this product for all ik greater than n, I with I not equal to k. So the second part is non-positive. Now let us look at our first part. Now I claim that our first part will go to 0 as n go to infinity. The trick is that we're going to majorize our first part as follows. There are two parts in our first part. Although there seems to be a double sum over two indices. Because n is fixed and I is taken from 1 to n, this double sum can be majorized to a single sum over k. So we are going to consider summation where I ranges from 1 to capital N, where n is fixed, of the probability of AI intersection AK, where we do not put any restriction on AK, except for it is between 1 and n, divided by the original denominator, the square of this sum of probabilities. This is the first part. And for the second part, we still do the same. The denominator is still the square of this sum of probabilities. And the numerator, there's h times the summation, where I is from 1 to capital N, and k has no more restrictions except for it is between 0 and n. It is between 1 and n of the probability P of AI times, and here we have changed the negative sign in the middle to the plus sign. Now, the numerator of the first part can be further majorized to the probability of just AK. Because previously you have the intersection, now remove AI. And you can do the same thing for the second part. You remove P of AI. So this will be just the summation of P of AK. Now, because I from 1 to capital N is a dump notation, we will take the sum of P of AKs. And same for the second sum. What you get is just a capital N multiple of the summation over k from 1 to n of P of AKs. So this whole thing will be equal to 1 plus h times capital N times the summation from k to 1 to n of the probability of AK divided by the square of the summation from k to 1 to n of P of AK. And this is simply equal to 1 plus h times n divided by the summation from k to 1 to n of P of AKs. So we get something that is really simple. By our hypothesis that the sum is infinite, this guy will converge to 0 as little n goes to infinity, with capital N fixed. Now we have shown the first part will go to 0 as little n goes to infinity, while the second part is non-positive. So, in the end, this opposite h is non-positive. And with this conclusion, let us move back to the proof of this corollary. Now we are going to use the remarks we made earlier. From the remarks above, since now opposite h is non-positive, then h is greater or equal to 1 automatically. It turns out that from here, we do not need the assumption that h is greater or equal to 1. That h is greater or equal to 1 automatically follows from the assumption before it, which implies that, by our argument, that outside h is less than or equal to 0. So it seems to be redundant to assume h is greater or equal to 1 for this corollary. We assumed that h is greater or equal to 1 here simply because we want to avoid the confusion for the conclusion of this corollary. because if h is smaller than 1, then this probability will be greater than 1, which is absurd. So it is still kind of necessary to assume that h is greater or equal to 1. Although this hypothesis already follows from the assumptions before it. Now, with this clarification, let us prove this corollary. By our remarks above, that h plus 2 alpha h is greater or equal to 0, together with this inequality, in the Petrov theorem, which states that the probability of an happening infinitely often is greater or equal to 1 over h plus twice of alpha h. So, by the Petrov theorem, the probability of an happening infinitely often is greater or equal to h plus twice of alpha h, which is greater or equal to 1 over h. This is because our denominator is non-negative, while 2 alpha h is non-positive by our argument above. So this proves our corollary. It shouldn't be hard for you to see that this corollary is a generalization of Borel Cantelli lemma without independence. Actually, what this corollary does is that it gives you kind of a quantitative version of the Borel Cantelli lemma. In particular, if the sequence of events are pairwise independent, then we can take this h to be 1 and get the equality for all ik's. And it follows from this corollary that the probability of an happening infinitely often is equal to 1 over 1, which is 1. So this corollary, due to Petrov, is really a generalized Borel Cantelli lemma.